Hello, and here's the next video on derivatives, and have a look at the list of um, functions that you can see there on the screen. Now, this list here, I'm thinking will look fairly unusual to you, but believe it or not, we already have the skills, the tool set, to solve every single one of those problems already. You might not be able to piece the pieces together, but you know everything that you need to know. So if you like, pause the video, have a go at them. If you can solve every single one of these problems, you can probably just fast forward to the end of the video and answer some of the questions at the end. But they might look a bit too unusual. So pause if you want to, and then we'll move on. Okay, so unusual, but doable. Let's perhaps start with the last one. Basically, by now you should be, thinking along the lines of, well, what can I do to get this into some sort of power form that I can use that rule in order to complete them, a polynomial or something similar like that. Well, if you're thinking that, you'd be right, but let's see it in action. I'm going to look at the last one first because it's kind of similar to what we've been doing. So it's f of x, let's write it up here. F of x equals, we've got x squared plus x plus 1 all over x. Okay, so first things first, x squared plus x plus 1 is not factorizable, not easily factorizable. So we're not going to be able to just put this into bracketed form and cancel out something. There's no common factor of x here to cancel out the x anyway. So whichever way you look at it, this is not something that is easily solvable. But I draw your attention to this kind of almost partial first step. And that is, if you remember at the end of the last video, maybe the second last example, I had a numerator and a denominator, and what I told you to do is perhaps separate out the different parts of the numerator and put it over the denominator and then go from there. We're going to do something similar. So, by the way, with these functions as well, in theory, we should go x is not equal to 0 because the function's not defined at 0. So there you go. So it's got a restricted domain, right? Anyway, so what I do is I split it up. We know that when we split things up, we simply put the denominator doesn't get split. It's just the numerator that gets split. So I've got x squared on x plus on x plus 1 on x. Now this is all good in that I can cancel this x here with and take out the squared bit. Again, just to explain again, x squared is x times x. So I've got x times x on x. The x's cross out and we're just left with x, which is why I just cross out the big 2 there, because effectively I'm saying I've got x left over. Okay, and then these two x's cancel out. Not much I can do with this at the moment, so let's just redo that. Go back to black. Okay, so we've got x plus 1 plus 1 on x. Now that looks like it's almost doable. I hope you can see. I mean, if I just do it with a little blue tick, it doesn't mean anything, but that can be derived. The derivative of x is 1. That can be derived. The derivative of a constant number is 0. This one can be derived, but it doesn't look familiar. But I wonder if you can work out a different form for 1 on x. What does 1 on x really mean? Okay, I'll give you a moment to think about it. Pause the video. Alright, so have you had any thoughts about that? If I can just refer you back to your index laws way back when. We did it in grade 9 methods, and you may have done it in grade 10 core, I'm not too sure this year. But, well, let's have a look at it. What does 1 on x mean? if I just use this as my scribble page here, let's have a look at some index laws. And we can see that we know this to be true. If I have a cubed over a to the power of 1 over a, we know that that would be a times a times a over a, and the a's cancel out, leaving me with a times a, which is a squared. I'm going to speed through this because this is stuff from last year. In general, if you think about that I'll be able to cancel down. If I had a to the power of 5 over a squared, then that would be a times a times a times a, 5a, all over a times a. Every a on the bottom would cancel out with an a on top, and that would give me a cube. In general, we said that a to the m over a to the n is equal to a to the m minus n. Okay, so how does that relate to what we've been doing? Well, if I have 1 over a to the power of n, well, 1 is just a to the power of 0, because anything raised to the power of 0 is just 1. So we've got a to the power of 0 over a to the power of n, which is equal to a to the power of 0 minus n, using that rule there. 0 minus anything is just the negative of it, and so we're left with a to the minus 1. So 1 on a to the power of n, sorry, a to the minus n. 1 over a to the power of n is equal to a to the power of negative n. So that's our extension to negative powers. So if I have 1 over a, that's equal to 1 over a to the power of 1, and 1 over a to the power of 1 is equal to a to the power of negative 1. Okay? Like I said, a to the power of 7 equals a to the power of negative 7. In general, we look at the power underneath the fraction, and we can make it negative, like so. So I hope you can see how this might be useful. In this situation, we've got 1 to the power of x here. So 1 to the power of x can be written as 1 to the power of x to the power of 1 over x to the power of 1, and then 1 over x to the power of 1 can be written as x to the power of negative 1. Now, once we've got it in this form, believe it or not, our power rule works just as it does for positive numbers. It will also work for negative numbers. So if I've got x to the power of negative 1, I just apply the same rule. So we've got f of x is equal to x plus 1 plus x to the power of negative 1. Therefore, f dash of x is equal to, well, as I said to you before, x when differentiated is equal to 1. 1 when differentiated goes to 0. X to the power of negative 1, we just follow through with the same thing. So it becomes negative 1 times x, and we subtract 1 from the power. I'll just do it in blue so you can see it. Negative 1 was what we started with. We take away 1, and negative 1 take away 1 is negative 2. So if the power is negative, when we subtract 1 away from it, we go further negative, right? So I guess the size of the number increases because we're going further down the number line. I'm just going to erase that though because it's a bit messy, but I'll put negative 2 there instead. Okay, so it's minus 1 times x to the power of negative 2. Let me just tidy that up a little bit. That's equal to 1 minus 1, so it's minus x to the power of negative 2. And that equals 1 minus 1 on x squared. So the derivative of f of x equals x squared plus x plus 1 on x is equal to 1 minus 1 on x squared. Now I guess if you really wanted to, you could put that as a, you don't really have to, that's fine how I've written it, but if you want to go crazy, you can say f dash of x is equal to x squared minus 1 on x squared. So I've just made it into a single fraction. If you're not too sure about that, do ask, but hopefully that makes sense. So there you go. So I guess the point of this particular one is that you can extend your idea of the power rule in derivatives to negative numbers. Okay, let me just do I'll just skip past these ones. So if I just choose a simple one, but if I had f of x is equal to 7 on x to the power of 6, say for example, then I would simply make that 7x to the power of negative 6. I would then go f dash of x is equal to, and I'll do this bit in my head, okay? So I'd go 7 sixes are 42, so it's negative 42, okay? Because it's a negative times a positive, and x to the power of negative 7. So I've subtracted 1 from negative 6 to get to negative 7. So the application of the rule is identical to the ones we've been doing in the past. It's just that you need to take special care because you're dealing with negative numbers. And again, I might leave it like that, or I might make it negative 42 on x and make sure you make the power positive again. If you're going to sink it down to the bottom, it's 42 over x to the power of positive 7. And that's it. I'd probably do it like that because then that form is in a similar form to the original form. Now, with practice, you can pretty much go from there to there. You can go, 6 sevens are 42, make it negative, but you can see, and then increase the power here to 7. So you can if you can sort of see it, that's okay. But I would suggest maybe doing these steps for the time being, because otherwise you will make negative number mistakes. It just out of carelessness more than anything else. So I would suggest you do the full solution like I've got there. Okay, so that's negative powers. Let's go back to the first page. So I'm hoping that sort of takes care of that, because I've just gone through it. That one, therefore, is a lot easier, isn't it? It's just a very simple version of what we've been doing. And it takes care of this one as well, although it might not look like it. So let's take this one and see if we can work it out. Okay, so having said that, I've probably just forgotten exactly what it was. So it was f of x equals, oops, wrong page. F of x equals 3x on 2 times 6 on x cubed. So 3x on 2, 3x on 2 times by 6 on x cubed. Okay, 6 on x cubed. Well, the answer, the first step, of course, is not to just go and try and work out the derivatives of all those little bits and pieces there. It wouldn't make sense to do that. I hope you can see that. What we do have to do is we have to simplify it. So using basic simplification techniques, 2 goes into 6 3 times. Let me see now. 3 is on top, so it's 3, so we can't cancel out that way. We've got an x on top and an x cubed on bottom, so we can use our cancelling down techniques there. So we can say x goes into x cubed. I might just cross out the whole thing. I could have just crossed out that little number and put a 2, but I'll do that instead on x squared. So what are we left with? We are left with 3 3s and 9 on top, and the 2's gone, so I'm just left with x squared on the bottom. So step number 1, simplify your function as much as you can. That's a good first step. And again, because I know I'm about to derive it, I'm going to change it into a negative index so that I know so I can deal with that a little bit more easily. Now I'm going to go f dash of x, therefore f dash of x is equal to, I'm going to multiply 9 and 2 together to get 18 and make it negative because I'm multiplying a positive by a negative. So I've got negative 18, and I'm going to decrease the negative 2 to negative 3. So I've got 18x to the power of negative 3, negative 18, sorry, which equals negative 18 on x cubed. And that's the derivative of that particular function. Okay, hopefully that makes sense. Alright, let's have a look at what we've got left. So that's those 3. These ones are got something in common, obviously, and that's the root symbol. Do note that without a number in there, it's a square root, so that's the square root of x. and in here that's the cube root of x. And I guess because this is a function, I should be at pains to say that this must be the positive square root of x. Okay, it doesn't have a negative there. It's defined as a function, not a relation, so we can talk about this as being the positive square root of x. Not relevant for the derivative work we've been doing, but I thought it's important that we do continue to check ourselves with that kind of stuff. Okay, so we've got the square root of x and we've got the cube root of x to the power of 5, and how do we do that? Well, let's just deal with a simple one first. F of x equals the square root of x. This requires you to understand what the square root means. Again, you have done this already. You should have done it in grade 9 methods, or if you didn't do 9 methods last year, you might have come across it in grade 10 core. What I'm about to show you is the simplest, smallest description of why the square root of x is what it is. If you don't get it, then I'll probably need to provide you with extra resources so that you understand it. So I'll do this with my scribble page over here. Okay, so what do we know? We know a few facts. First of all, if I multiply a squared by a cubed, that's a times a, and then I've got a times a times a. In total, that's 5 repeated multiplications of a, which is what a power is, so that's a to the power of 5. In general, a to the power of n times a to the power of m is equal to a to the power of n plus m. That's the way it rolls. Okay, so let's have a look at the square root of x. What do we know? Any number, if we square a square root, we get the thing inside. Okay, so if I square root x and then square that, I get back to x. All good? Okay. A square simply means root x times root x. So root x times root x equals x. X is a power of 1. So, what power would square root x have to represent? What power would the square root have to represent in order for this to be true? So, x to the power of what times x to the power of the same thing has to equal x to the power of 1. Okay, so if I just look at the powers now, so I'm zooming up at these powers here. I'm looking at this, and oops, daisy, and this. I'm looking at those three powers there, and using the rule that this plus this has to equal this, then I must have 2 lots of that question mark equaling 1. So what would that question mark be? A half. Okay, so that's the very short answer to how square roots work. And you can use a similar logic for cube roots, fifth roots, 100th roots, whatever you use. So in general, what do we have? Well, the square root of a is equal to a to the power of a half. Okay. The nth root of a, remember that's not n times the square root, that is the nth root. The nth root of a is equal to a to the power of 1 on n. Okay, cool. Well, what about a to the power of m? What if we take the nth root of that? Okay, well the nth root of that would be a to the power of m to the power of 1 on n. And then what we do is we end up multiplying these two numbers together. So we've got a to the power of m times 1 on n, which gives us a to the power of m on n. So, like I said, this was done in methods, grade 9 methods. If this is completely unfamiliar, foreign to you, you just need to let me know and I will find some resources which support in a much slower fashion how these things work out. The only thing I didn't really explain hugely is that this relies on this particular rule called a to the power of m to the power of n is equal to the power of m times n. And that can be proven in a fairly similar, not proven, but at least demonstrated in a fairly similar way to perhaps this rule here. So maybe with a bit of thought you could work it out, but if not, just let me know and I'll sort you out. Okay, so how does this relate to everything that we've got here? So f of x equals the square root of x. Well, quite clearly then, based upon what we said before, that this can now be written as a fraction, x to the power of a half. And now we can apply the power rule exactly the same way as we have for every other situation. We derive it like so. F dash of x is equal to a half times x to the power of a half minus 1. Just like we've done all along. The number that we start with becomes multiplied at the start, and the power gets 1 subtracted away from it. So what does that look like though? That equals a half times x to the power of negative a half. A half take 1 is negative a half. Okay, that's not in its prettiest form though. Remember, a negative power can be made positive by putting it as 1 over. So it's a half times 1 over x to the power of positive a half. And then positive a half simply means square root again. So we can actually go 1 times 1 is 1, and 2 times x to the power of a half is 2 root x. That's a big 2 there, so it's 2 lots of root x. So if f of x equals the square root of x, then the derivative of f of x is 1 on 2 root x. And that's how you do it. Now, looking at a final example here, and the final example is the cube root of x to the power of 5. So let's write that out and we'll go from there. So f of x is equal to the cube root. That's not 3 times the square root, that's the cube root of x to the power of 5. So the first thing we do is we convert this into a fraction power. So that's equal to x to the power of 5 on 3, like so. And now when we derive it, it's all hopefully plain sailing from here, as long as you're okay with your fraction work. F dash of x is equal to 5 on 3 times x to the power of 5 on 3 minus 1. Because it's fractions and you can't just do it, I mean, you probably can, but it might be a bit tricky to do in your head. I just tend to take 1 or 2 extra steps to make sure I'm not mucking things up. So I don't do 5/3 minus 1 in my head. It's not that bad, but I just don't do it. So that's equal to 5/3 times x. So 1 is 3/3, so 5/3 minus 3/3 is 2/3. So it's x to the power of 2/3. And now I'm just going to change it back with my root notation. So that's equal to 5, and x to the power of 2/3, it's already positive, so it stays on top. So that's 5 cube root x squared over 3. So a bit horrible looking, but nevertheless that's the derivative. So when f of x equals the cube root of x to the power of 5, then f dash of x is equal to 5 times the cube root of x squared all over 3. And that's basically it. So with this last example here, we've now extended our power rule to looking at indices which are negative and indices which are fractions. And that should be enough for you to have a go at doing some problems of that nature.